So Rose, if you are ready, you may start.
Okay, thank you. All right. Hello, everyone. Reina and Fernando. Thank you for coming to my capstone presentation on mapping the retreat of the debris-covered Tasman Glacier in New Zealand. To set the mood, here's an image of the Tasman terminus. So why glaciers? Well, in the context of rising global temperatures, mountain glaciers across much of the world are retreating and impacting the water supply for billions of people. Unfortunately, there's no climate policy today or in the future that will preserve many of these glaciers, as many of them will simply disappear by the year 2100. To mitigate the impact this will have on the local communities that rely on this gradual supply of glacier meltwater, it's essential to establish a means to measure, model, and plan for future climates. This study is motivated by the measurements needed for the long-term analysis of changes in glacier extent, and specifically the challenges in obtaining these measurements from debris-covered glaciers. Okay, for this slide, I'm doing a 2-for-1 and fulfilling my cartographic duty while also listing the objectives for this study. There are 3 main objectives, and they are to measure and map the debris-covered portion of the Tasman Glacier, and to measure and map the extent of the proglacial lake that's resulted from the retreat of the glacier. And lastly, to create outlines for the Tasman Glacier system using the Glims outline as the template for the upper part of the Tasman Glacier. All right, taking a quick look at the map, the Tasman Glacier is located on New Zealand's South Island, east of the main divide of the Southern Alps in the Arauki Mount Cook National Park. And this is the entire national park here. It's considered a compound valley glacier. For a bit more perspective, there are over 3,000 inventoried glaciers in New Zealand. The Tasman Glacier is the largest. Its main trunk, which is here, flows south from the accumulation zone from about 2,300 meters down to the terminus location, which is the current location at 707 meters in elevation. The retreat of the Tasman Glacier can be traced to the 1960s when they first observed the first surface drop. And after that, in the 1970s was the superglacial ponds forming on top. And then in the 1990s, some of these ponds coalesced to form the proglacial lake. And soon after, the rapid calving of the terminus ice cliffs into the lake began. All right, in the interest of time, I'm going to mention the main hindrance in mapping superglacial debris cover using satellite data. If you take a look at this image here on the left, what we're looking at is a debris-covered glacier. This is not the Tasman Glacier. This is the Hooker Glacier, which is just on the other side. But it's a very good example to demonstrate the issue. So if you look at the surface of this glacier here, which is here, its hummocky surface color looks just like the color of the moraine walls, which are here. And this is the problem. In a multispectral analysis, this translates as a spectral similarity, making it very difficult to draw a boundary between that moraine and the glacier, much like the similarity between the spectral signature of water, ice, and snow. So with this challenge, the decision to take the machine learning route for image classification was made. All right, so now let's take a look at the data that was used for this study. Landsat Collection 2 Level 2 surface reflectance images were obtained from the USGS Earth Explorer website, all analysis ready with a 30-meter spatial resolution. There are 4 sets of images comprised of multispectral bands and a thermal band from 4 different sensors. The images are from 4 different timestamps with an approximate decadal interval between 1990 and 2022. Also, the images were chosen within a 4-month window between the start of summer and mid-autumn to ensure seasonal snowmelt. Next, 2 Aster Global DEMs were obtained from the NASA Earth Data website, and they also have a 30-meter spatial resolution. And lastly, the Glims 2013 Tasman outline was also obtained from Earth Data website. All right, now let's take a look at the methods used. This is a primary workflow, and it breaks down into 3 parts. In short, the pre-processing involves fixing no data pixels and clipping the resulting images to the study area and then compositing. The machine learning workflow is the brains of the study, and it involves creating a schema comprised of classes we want to classify. In this case, it was a 5-class schema for water, snow, vegetation, debris cover, and other debris. Once the schema has been decided on, the next thing is to create the training samples for the machine learning. And this involved manually digitizing over 2,500 polygons. I'll go over the rest in a bit, but for now, I just want to point out that this entire workflow is robust, it's reproducible, and it's possible to automate using code, with the exception of some reference data for validation and the actual manual delineation of training samples. So, following the workflow, in brief, I'll mention the pre-processing again, which entailed fixing no data pixels using Nibble. And the way Nibble works is by replacing cells of a raster corresponding to a mass with the values of its nearest neighbors. Post-nibbling, all raster images were clipped to the Tasman study area and composited. And lastly, the 2 DEMs were mosaicked and clipped to the study area to generate a slope raster. So before continuing with the primary workflow, I briefly want to go over the contextual workflow, which consists of generating mean NDVI and NDSI binaries. And this was done mainly to assist me in interpreting the region and learning the extent of the snow and vegetation cover. They also supported the development of the 5-class schema and site selection for training samples. And lastly, the glacier watershed was produced for a general understanding of how and where the large tributaries are in confluence with the Tasman Glacier. And it's these here with the dots. And here's an image of the NDSI and NDVI for reference. All right, now to the brains of this study. I briefly went over the process of creating the schema and creating the training samples, which are then used as input, along with a composite raster and a slope raster to train the SVM classifier. In the training process, the SVM draws a decision boundary, also known as a hyperplane, between any 2 classes in order to either separate them or to classify them. This diagram represents a linearly separable scenario, but in the real world, data is randomly distributed, and it makes it really hard to separate different classes in a linear way. But the SVM classifier in ArcGIS Pro uses an RBF kernel, the radial basis kernel, to mathematically trick the process into computing in higher dimensions. So once the classifier is done learning, it produces a .ecd file, which stands for Esri classifier definition file, I think. It's basically a JSON file, and it contains attribute information, statistics, hyperplane vectors, and it'll use this information for the actual classification. So once we have that .ecd file, it then is used as input for the actual classification, along with the composite raster and slope raster. And here we have the results of the actual classification. And where you can see this light blue represents water, the darker blue, snow and ice, and the green vegetation, and the mustard color is debris color, and that off-white is other debris. And you can clearly see where the snow is. You can clearly see the Tasman Glacier, which is right at the center. And you can see that it picked up other glaciers in the area as well. And yes, those other glaciers are known debris-covered glaciers as well, to include the Hooker Glacier that I demonstrated in the image earlier. So to quantitatively assess the classification results, accuracy assessment points were generated using a random stratified sampling strategy with a minimum of 500 points for validation. And then they were validated against the original false color composites. Using the validation results, a confusion matrix was then computed with evaluation metrics, and they are down here. And in brief, the overall level of agreement between the ground truth data and the predicted classes using the SVM classifier is strong, with an average kappa statistic of 85% and an overall average overall accuracy of 90%. So post-classification, to remove the single misclassified pixels in each classified image, one pass of the majority filter is applied. Following this, the classified rasters are converted to vector images for extraction of feature classes. These 2 images show here are the feature classes for water and debris. And after after isolating each feature class, then there was further extraction of the actual contiguous debris cover for the Tasman Glacier and for the Tasman Lake. All right, this is a pixel for pixel area calculation using the contiguous area extracted from the classified vector image. Overall, there's a general decreasing trend in the area calculation, except for the year 2000. We see that it seems to increase from the year 1990. And I got the blue card, I was distracted, but really this has to do with the amount of snow in the year 1990, which actually turned out to be twice as much as for the other years. So indicating that the debris covered area is most likely greater than what we actually see. Overall, the debris cover, a 3.8 square kilometer area decrease is calculated between 1990 and 2000. And here is the terminus, and we can see that it was definitely retreating. All right. Oh, one thing about the debris cover is that overall the debris, well, there was no direct comparisons of the debris cover areas in the literature. However, the area calculations in the study are in the order of magnitude seen for other total areas and percent debris cover areas with different timestamps. All right, as for the proglacial lakes, we can clearly see it expanded, and by as much as 6.5 square kilometers, which translates into an 81% increase in surface area. Direct comparisons of the lake surface area were found in the literature for the years 2000 and 2010, and they compare very well within plus or minus 0.04 kilometers squared. All right, two maps were created using the calculated areas. One is a map of the terminus position. The other map is of the proglacial lake extents. The surrounding features here were digitized using the slope and false color composite rasters. But here we can see for the terminus map, the 1990 terminus position, the 2000, the 2010, and 2022. And of course, we're going to see just the opposite for the lake. It's expanding. So here's the extent of the lake in 1990, 2000, 2010, and today, 2022. This is what the extent of the lake is, this entire region here. All right, the outlines for the Tasman Glacier were completed assuming no change to the upper part of the glacier and using the Glimpse outline, which is this one. This is for the year 2013. You can see the terminus is between 1990 and 2022. It's kind of looks like this one here, but it's different. And once I had those outlines, I was able to actually calculate the area for the entire glacier system. And then from that, calculate the percent debris cover. So in conclusion, the debris area cover was measured and mapped to show that the retreat of the Tasman Glacier terminus, the proglacial lake extent was measured, mapped to show that the Tasman glacial lake underwent a major expansion in that period. And lastly, the Tasman Glacier was delineated. Total area of glacier was calculated, and the average debris covered area is 27% of the glacier. Recommendations: add more variation to the data to include a larger temporal range and more seasonal variation. Extend the study to include other glaciers in the area, because as we could see, it clearly picked up the other glaciers. So it's very possible that at this resolution, we could study those further. Investigate other tools for filling no data to exclude any possible bias. Thank you, Fernanda, for that. And test other classifiers and perform quantitative comparison tests to assess performance and reject the null hypothesis or not. And something that this study did not do is to explicitly quantify uncertainties. Well, that concludes my presentation. Thank you.